Welcome. Today is Tuesday, October 2nd, 2018, and this is the NHERI webinar series. For more information on the SimCenter and the NHERI project, visit the NHERI website at DesignSafe-CI.org, where you can find links to the SimCenter and the NHERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructure's Computational Modeling and Simulation Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today we're joined by Stella Yu. She has a joint appointment in the Electrical Engineering and Computer Science Department at UC Berkeley and at the International Computer Science Institute headquartered at UC Berkeley, at Berkeley. At ICSE, she directs the Computer Vision Group and teaches machine learning and computer vision on campus. The title of her presentation is Deep Learning for Structural Engineering. And Professor Yu, I invite you to begin.
Thank you, Matt. So today I'm going to talk about 4 parts of materials. The first one, I'm going to tell you some of the examples in my group about applying deep learning to different domains. Then I will cover some basics of deep learning. And in particular, I will talk about our latest research on learning from big data, but no annotations or small amount of annotations. It's a misconception that for newcomers, people think that deep learning always needs a lot of annotated data. And we are making headway on that aspect. I would like to share our latest research on that. The last one is, as part of the AI team on the NSF SimCenter project, I would like to sketch what goals we want to achieve in this project. We have a project with the Lawrence Berkeley Lab, and it's about developing a screening tool for X-ray crystallography. When a crystallized molecule is presented, X-ray shoots light on it, and it creates a particular diffusion pattern, diffraction and diffusion pattern. And depending on how the molecule is presented, what film is used, the images could be drastically different. For human eyes, if you want to detect a pattern, something they call Bragg's peak, you have to detect tiny dots first, and then you look at the pattern these tiny dots form. It's a very difficult job, even for the human eye. They have a particular viewer, you have to zoom in, zoom out, and there's huge varieties due to the film choice, the device used to present the molecule, and all. So our challenge is, despite all the varieties, we need to come up with one universal algorithm that can make a screening whether this image contains Bragg's peak or not. The NSF SimCenter project, in the project, we want to understand how a building will shake. This is the pipeline taken from the project overview slides. We want to simulate earthquake events, and we can generate site-specific ground motions. And if we have a building model, we can simulate structural response, and then a lot of things can be done. For example, estimating loss and assess the regional risk. But our role in this project is we don't have the structural models. How can we get such models? So there's a third column in this slide. If we are given a building information model like this one for a frame, this model is given to different engineers, and no two structural engineers will come up with the same structural models. And it takes them months to come up with such a model for each of these building information model. Our job is to turn this, this human expertise required model extraction, model building process into an AI algorithm. This AI algorithm will behave like, split personalities. It can pretend to be engineer A, engineer B, and maybe some virtual engineer. These will be plausible model, and that's our goal, is to generate the structural models automatically. We also have a Samsung project. Samsung is looking for the next generation mobile communication. We all have the experience. If you go into San Francisco, all these high rises will have impact on your cell phone reception quality. What they have done is they, at each location, they will evaluate how the signal. So you have somewhere TX, and at each location, receiving location, RX1, RX2, RX3, RX4, they will have measure the quality of the signal. You can see that there's a loss of quality at the different locations. And that has something to do with the geometry, also has something to do with the materials, material property. For example, bricks, windows, concrete materials will have a different impact on the loss. So Samsung wants to build this city scale level simulation environment. They can predict how much loss, which places suffer the most loss, so they can place place a transmitter strategically and find ways to cope with the loss. But how can you get the material properties? That's where we come in. What we are doing for them is, let's say you have a lot of Streetview images of the city, Google Street Views. Given this, we can have people annotate some material qualities of interest. For example, trees, curbs, sky, windows, concrete, wood. And we can perform material segmentation on these images. And for city scale modeling, this may still be too slow. It's impressive, these results are impressive, but it's still too slow. So the next stage in this project, we try to predict the material quality from satellite images, from aerial views about of the area. For example, given the satellite image, we want to predict whether the building is mostly concrete or mostly wood houses. And once we have such information, we also detect a glass, whether the pixels indicate something made of glass. We can actually give 3D models which you can purchase. There are a lot of companies building 3D models of buildings, but they just have a simple models without these so-called microstructures. These windows, they don't mark out these windows. Because we can detect materials, we can actually create these very detailed 3D models with windows marked. Another project is in the medical domain for Glidewell dental labs. They dominate the US market on the dental products. If you have a friend who misses a crown, usually you go to dentist's office, the dentist will take an impression of the missing crown. And then this impression will be sent to a lab. Most likely it's Glidewell dental labs. They occupy like 90% of the market in the US. And a technician in their lab goes through years of training. This is just one page from their manuals. One of the design rules will say, okay, how they should be aligned, vertically, horizontally, what makes it aesthetically good looking while functional. Because this process requires customization, every patient's tooth need to be reconstructed. The whole process has to go through a pipeline of manual interactions, even with the computer-aided design and computer-aided software. So you can see there are a lot of technicians involved, and every step on the way, not just designing the geometry, but also say the color, the choice of color, and a lot of processing following that. Because they need to use the CAD software, they already built a data set where the impression comes in, they do the 3D scanning. So they know the so-called prepared jaw, where there's a missing crown on the side of the jaw. They also have the opposing jaw, the 3D impression. And then when they design the CAD software, using CAD software, they have the one with the crown filled. So we started by looking at the data they have. We turned it into a 2D depth image using some reference plane. So this is prepared by their technicians, and they give us the data. The 3D model becomes a 2D image for prepared jaw, opposing jaw, and then the designer crown. So we thought, what can we learn from this? Can we use what they have in stock and learn our algorithm, takes these first two as an input and predict what the missing crown should look like? So that's the first thing we have done. Shown here are two examples, one row per example. The one in the first column, outlined in green, that's the input with the missing crown. The one on the rightmost is the technician's design we use for training. Images like this are used for training. This is a test case scenario. The middle one is our prediction. Second row, likewise, you have some missing crown. You have the technician's design and our prediction. We worked 6 months on this project, and when we predicted produced our predictions, we did 3D printouts, and we give our printed design and their technician design to their experts, and they cannot tell the difference. This is when they realize there's something going on with AI, and it could have made a huge impact. But that's just a first step. We just capturing the expertise of technicians with machine learning systems and learn a predictor that can reconstruct crowns. Next, we said, can we do better than that? The technician, who says technician designs are the best? So what we do is this. We have some good jaws, right? Always have opposing jaws. These are the good ones. We do segmentation on one of the teeth, and we carve it out, leave it out as input. So this is a missing crown. On the left, the rightmost, you see the natural tooth. And we use this, we want to predict the rightmost crown from the one on the left as the one with missing crown. The middle column shows our prediction results, and the second row shows another example. So the challenge in those dental industry and many other medical domains is how to design something that's, not just best in terms of functions, but it's something that fits you, right? It's really a mass customization required in creating such products. And the next thing we've done, we take this research to one step further, is to say, there are things that, whether human technicians are not good at. One example is the surface of the crown. Those grooves you have, as people age, the grooves will be worn out. And you can design some crown that fits in the cavity, but that crown may not be guaranteed to work well with the opposing jaw, because the tooth needs to be mobile during chewing actions. And the contact with the top surface needs to be sparse. It's not a perfect fit. You cannot have contact everywhere. You only have few points of contact. That allows you to chew more effectively. And that's very difficult for humans to design. So we thought, how can we capture that, the dynamics, the functions required for this for the dynamics of functioning. So we come up with a statistical feature. The natural teeth, if they are developed for the sake of these actions, there's some statistical feature we can collect. And we are going to generate this crown that conforms to the statistical distribution on such features. So we learn from big data. We started from learning from technicians. It's supervised learning. It's just memorizing the expertise, capturing expertise. The second step, we go for learning from nature to more natural crowns. And the third step, we design new loss functions that capture the functionality loss. And we can learn from big data for more functional crowns. And this was featured in the NVIDIA GTC conference this year, and we received quite media coverage on this work. The next example is about is a collaborative project with the UC Berkeley's Eye Center. There's something called meibomian glands, which is crucial to secrete oil on your eyelid surface, so you don't experience dry eye. If the glands are impaired, then you have dry eye syndrome, a lot of discomfort. Their technicians receive such instructions. They rate the quality. They do this meibomian gland imaging. And if the atrophy area outlined in red, this is atrophy, the glands are kind of degenerated. If the area in red compared to the whole eyelid area is less than third, it's mild atrophy. There's no atrophy, there's mild atrophy, and the next third will be medium atrophy. Last third will be severe atrophy. Technicians are given such instructions, given examples, and then they go on this categorical rating. So we thought if we have such annotations, we know which areas are in atrophy, which areas are normal eyelid area, we can train a network to learn that. The first column is input image. The last column is the ground truth annotated by technicians. And the middle column is our deep learning network that predicts the eyelid area. We do the same thing to the atrophy area. First column is image. Last column is the technician annotated atrophy areas, and the middle column is our prediction. So we learn from such data. When we produce these results and show these to our collaborators, they said, wait a minute, if you look at the second row, there's a spike on the right, yet it's missing in the prediction. And they looked deeper into this image, take a closer look at the image. They said, actually, the annotation was wrong. This turns out to be the gap between two glands. There's no gland atrophy per se. So although our algorithm is learned from these faulty human annotations, because we learn from a lot of such annotated images, because we learn from different technicians, there's this wisdom of crowd emergent from this big data, and it can correct the mistakes by individual technicians on specific images. And once we have this numerical rating, since we have the area for atrophy, area for eyelid, we can calculate numerical rating. And we can come back to rate how human technicians are doing. Human technicians give this categorical rating, no atrophy, mild, medium, severe atrophy. You can see that humans are essentially overestimating the severity. Ideally, you want all the red dots go to the rightmost column. So overall, human accuracy is only, excuse me, 83%. And the machine accuracy, easily 95%. More than that, we are working on segmenting individual glands out and collecting statistics on this. So these are actually very challenging tasks because the glands are not well demarcated in terms of image appearance. So with the deep learning and the new capacity in computer vision, we are hoping to do better and a new science. So I've gone through some of the examples in terms of application in my group. You might wonder what's common across all these data domains. I give examples on scientific imaging data. There are a lot of varieties. Some may be exploratory. LBL is churning out a lot of images, larger, better details, but they don't have algorithms to follow up, to analyze these images. And sometimes you don't know what you're looking for. You have some knowledge about the physics, but you don't know what kind of patterns, how many kinds of patterns exist in such data. Engineering data, usually you face large scale data problems, and the cues could be rather weak. For example, the material segmentation in images. How can you figure out the material based on just single shot of the scene? The medical images, it really requires mass customization. There's actually, in terms of problems, there's nothing common across these data domains. But in terms of what's involved in the modeling, there are some commonalities. One, all these problems require human expert annotations. When human experts are involved, usually the annotations are noisy and a small size because it comes with a cost, with time and expense. And sometimes you don't have any annotations, for example, in exploratory data analysis. The second thing is we really need an algorithm that can bootstrap from such small annotation and extrapolate beyond what you see in the training set. From these examples, I hope that I give you a sense that with big data, we also need to think big. We don't try to do the supervised learning. Whatever the annotation you get, you just try to summarize, capture that. We need to think big with big data. We need to learn beyond annotated data. So what is this machine learning? What is this wonderful new thing that has made quite waves in computer vision and deep learning and many applications, many domains. In the machine learning class we teach, this is the first lecture we give. What is machine learning? Machine learning is about predicting Y from X. When we are given an application, the first step is to turn the data into a feature vector space, X and Y. You have to turn into numerical representation. That requires a lot of expertise and a domain expertise. This is where the machine learning experts have to work with domain experts. Step 2 is to choose a loss function that can measure how well a model, f of X, predicts Y. Step 3, you pick a family of functions that might predict Y from X. You look for the best function within that family that predicts Y. Step 4 is you collect a lot of data examples, say n examples. Step 5 is to minimize the total loss over all the examples. This is optimization step. Last step is very important. Once you have the optimal solution, what do you do with it? You have to evaluate the optimal model on new data. okay? A simple example that follows this recipe is line fitting. Let's say, you know, we get some data from some applications. We already have done the step one, turning this into feature vector. We have some 2D data points, X and Y. And the loss function is a, you know, mean squared error between the predicted value of Y and the ground truth Y. The family of functions we pick, say, is all the lines in 2D. We don't have to do that. We can choose quadratic family. We can choose cubics. These are all choices. Let's say we choose lines. And then we have all these examples, and we minimize the total mean squared error over all these examples. That gives us a least square solution. That's the optimal solution. Now we have a line. The step 6 is to evaluate this line on some data you have never seen during training, and that gives you a sense how good your model is. Remember, machine learning is about prediction. Fitting the data, you can think of, if I pick a family, it's about system identification. That's of less interest. How well you can predict the future data is of importance. So I give you an example on classifying image into the semantic types. On the left, you see that there's image. My input is image. That's my X. Y is a semantic label called bike. Okay? So step 1, you have to turn into a numerical representation. For X, it's just image. It's a 3 slices of 2D arrays, each array for color channel. So you have red, green, blue, and each is a 2D array, number of rows, number of columns. Y is a bike. It's a semantic label. We are not fitting against these words, strings. We turn it into some representation. If I have 1,000 categories, I'm going to use a vector of 1,000 dimensions. If it's class 1, I give it 1, 0, 0, 0, all the way 999 zeros. It's called one-hot vector encoding of class. Okay, so why do we treat this as classification problem? Because we treat them as discrete concepts. They are not related to each other in certain way. They are just different. Okay, so one-hot encoding reflects that. And so-called deep learning is you have the input, the image as input. It goes through several processing called convolutional layers. First one, C1, go to second one, C2, C3, C4, C5. Convolution, essentially, I have an image of certain size. My filter is, say, 3 by 3. Okay, I can compute the average intensity in this 3 by 3 window. That's a filter. The filter essentially has equal weights, and each weight is 1/9. And you can have difference filter. Say you want to detect a vertical edge. Then the left 3 is in a 3 by 3 matrix. You have -1, -1, -1 on the left, +1, +1, +1 on the right, and the middle column could be 0, 0, 0. That's a filter. It's calculating the sum of intensity on the right minus sum of intensity on the left. So that's, if there's large value, meaning there is a good chance there's a vertical edge between left and right. Okay, so, and once you have C1 to C5, 5 convolutional layers, you can choose. Each filter will give you a feature response. If you choose 100 filters in the first block, C1, you're going to have 100 such channels of responses. Likewise, once you look at these filter responses, you can again apply convolutional filters on the feature maps, because each feature map is an image as well. So you do this 5 times, okay? And then you go to the so-called F6. These are fully connected layers. In convolutional filters, each filter may be just 3 by 3. And every pixel, you calculate the 9 by 9, so 3 by 3, 9 value average, for example. For the fully connected layer, each node, the response, looks at the entire response. So every node in the previous layer connect to that output. So if you have, say, 4,000 such fully connected nodes at the FC6 layer, earlier you may have, say, for images, you downsize at the end, maybe 25 by 25 times 200, so 512 channels. At the end of this, you get 1,000 responses at FC6 layer. And you do it a few times, 3 times illustrated here. And that becomes you output your prediction in this 1,000 dimensional space. And you measure this against your ground truth label. It's a bike. Let's say it's represented as 1, 0, 0, 0 all the way. And your prediction may become 0.8 minus 0.1, 0.05, so on and so forth. You measure the loss with a certain criteria. For classification, a commonly used the softmax loss. And then you have an error. So during training, you look at the error and say, how can I reduce error? So there's something called backpropagation. Essentially, the resulting error on the final prediction is this much. Now I'm gonna take a step back, say, how should I distribute these errors? Who I should blame the most? So what's done here is, in the forward path, you compute from image X all the way to the loss function error. In the backward path, illustrated in red, is you look at error, say, maybe in FA there are 4,000 weights. Which weight should take maximum blame? How shall I adjust the weights in order to minimize this error? So this will be partial error over D error over DW8. And then you can, once you figure out each weight, how they should take the blame, you go one step further, say, you look at the W7, how much should I adjust W7 to reduce that error? So on and so forth, all the way back. So this is how you update the weights during training. If you look at the pipeline, the key thing with deep learning, why this is called deep, is that it's extracting features of features. It's a compositional models, as illustrated here. You start with X, you first calculate C1 of X. It could be calculated the mean intensity, the edges, and the next stage is you look at all these edge responses and say, is there a corner? Is there a junction? That may be done by C2. Then you look at the C3, is looking at what can I do? Can I detect some texture? So the feature become more and more complicated. The complexity of feature builds up as you move along the network. And each feature in the convolutional layer, if I have 100 feature channels, each feature will be used everywhere in the image in 3 by 3 window. That's why it's called convolutional. Even though the filter is 3 by 3, it's applied everywhere. You look at the pixel, you impose a 3 by 3 window on that pixel. With that pixel as a center, you calculate the value. You move to the next pixel on the right, you do it again. And you do the scanline fraction. There's a fast algorithm to compute that. But conceptually, it's applying the same filter everywhere in the image. So these are the model parameters. So these weights are shared in the convolutional layers. And then in the old days of computer vision research, what feature to use is highly critical. If I have learned how to do tracking, the features used for tracking may not be useful for object recognition. It's a big expertise to develop over years of studying in computer vision. But now with deep learning, the bar has been lowered. You have a lot of data, just images and their semantic labels. You construct your network architecture like this. All the weights are to be learned. And they are learned end-to-end, so-called, from input out to the output jointly through this error back propagation. Once this is trained, you have a hierarchy of representations, starting at the beginning of pixels, intensity of pixels, to low-level features like edges, corners, blobs, and then to a higher level of object parts like eyes, some contour fragments, and then to even higher level objects, to scenes, okay? So essentially the representation is transformed from very low level description to very high level descriptions. Because in the end, you want to map an image into the semantic label representation. As you approach the end of the pipeline, you understand, the computation understands the semantics. And this whole learning process takes a concrete input data into some abstract output space. So that's the common so-called full image classification task that made deep learning famous. Prior to deep learning, we are looking at image classification at certain accuracy level, and even 0.5% increase in accuracy is considered a good improvement. When deep learning approach is applied to that task, we are observing 10% improvement. Deep learning has been going on for a few decades. It's that large scale application image classification made people realize we have to take neural network approach seriously, because all the smart people work on the problems can only get a 0.5% increase, while deep learning without much thinking, just with the the architecture deeper, with big data, with a GPU, the availability of the GPU compute resources, we can deal with more data. We can deal with more complicated networks, the deeper networks. We can achieve so much better in the performance. Nowadays, the full image classification can achieve so-called superhuman performance. There are other problems, common computer vision tasks people have studied. Aside from full image classification, essentially you want to make one assertion about the entire image. There are so-called semantic segmentation problem. Given an image, you want to label this as which pixels is grass, cat, tree, or sky. You want to segment them into groups by the semantic labels. And there's another task called classification and localization. You want to detect all the objects instances not as complicated as segmentation. You don't have the details, but you have a rectangular box as a proxy. This is called detection task. You localize where the object is in the image. This is the localization classification. The detection, you want to get all the incidents out. And then the last one, instance segmentation. The difference between instance segmentation and semantic segmentation is, in semantic segmentation, if I have two cats next to each other, they will both be labeled as cat pixels, but they don't know one set of pixels belong to cat 1, the second set of pixels belong to cat 2. So instance segmentation is a much harder problem. So all these the applications you have seen at the beginning, I talk about, they fall into these 5 buckets. In terms of tasks, it could be classification problem, could be segmentation problem, could be a regression problem. Regression is, instead of saying which label, class label, you want some specific quantity. For example, from given a color image, RGB image, I want to predict each pixel, what's the depth associated with that pixel. It's a value. It's not just, you know, a particular label. Then there's detection problem, object detection. And then there's 3D modeling problems. On the surface, they show up as different domains, different tasks, but from, you know, in terms of vision and the learning problem, it falls into one of these tasks. It encompasses this, this view of looking at the problems can help you understand what problems should be formulated as what kind of tasks. So in my group, I focus on the representation learning and the integration learning. How do I learn to integrate information from different sources? And specifically in terms of research, I'm interested in how can I extract information from multiple scales. When deep learning requires a lot of data, if and the ground truth annotations, if I don't have that, but I have synthetic data where I know everything, how can I train a network using synthetic data? But having a model predict synthetic data is of no interest. Such a model that's learned, when eventually I want to apply to real data. And the synthetic data and real data may have a discrepancy in the appearance. So how do I accomplish this domain transfer? And a lot of data are not just real value data. Some may have complex values. For example, radio frequency data, magnetic resonance image data. These are naturally complex value data. And before deep learning took off, people always think about the representation. The highlight point of signal processing is Fourier transform or wavelets. These are complex Fourier transformations in complex value representation. With deep learning, people love the idea of this end-to-end learning. They don't think about representation anymore. But for some applications, say the spectrum is more important, more indicative, more relevant for the task. Why not use that? But how do we integrate this into deep learning platforms? This complex value. The third thing is that this low shot learning. What if you don't have a lot of expert annotations? Is this the bottleneck? But I may be easily get a lot of unannotated data. Big data is not an issue. Annotated big data is an issue. Last thing is about graphical data. Not all the data can be represented in the fixed length format, not image a certain size, or even for language, you can presume it's maximally it's certain length. How, for example, there's some, data natural represented by graphs, social relationships. So these are I listed the 5 points of interest in my research group. Today, I'm just going to talk about one, the low shot learning, since I illustrated, lack of annotation is a big issue in all these applications. I'm going to talk about one work, the latest work we have. The setting is the following. If I have a lot of data, just images, this is actually examples from so-called ImageNet. They have 1.2 million images. I don't have any labels. I don't know what's in there. My question is, given such data, can I, after I have seen such data, can I come up with a natural visual similarity measure? Can I learn that? That's a challenge. So what you see here is 2 examples. The first row is a query image. Let's say you have some, you give a system this query, and you have all these 1.2 million images, and say, give me the closest looking images from this data set. The first row you see here is just based on color similarity. Every pixel has red, green, blue, RGB values. You just calculate the difference between each image with a query image. You sum up the error, and you pick the smallest one from this 1.2 million images. And what you get are these. They sort of pick out something, a white object in the center of the image. But if you look closely, other than that, they have no sense of visual similarity, right? It's just something white. It could be a cell phone, it could be a person, it could be a dog. That doesn't conform to what we know of visual similarity. The third row you're seeing here, the second row, is completely supervised learning. I have these images, and the ImageNet data set is labeled by humans. Say, this image may contain a dog, a cat, a tiger, okay? They are semantic labels. And I can use the example, the first example, give full image classification. I can train a network to predict the semantic label given an image. Once I finish training, I can look at the last layer feature representation. I use that feature to compare who has the closest feature to the feature of the query image. These are the retrievals. So you can see that they sort of pick out the same model in different poses, and there'll be other women wearing this dress. What we have done, this example, the second row results is come from unsupervised learning, meaning I'm just given these data without any labels. And we developed a learning approach that essentially treating the unsupervised learning as a supervised learning, but try to distinguish all the instances. If I have 1 million images, ImageNet has 1,000 predefined categories. Our work is to treat this learning without labels as discriminating 1 million images into 1 million classes. Each class only has one instance. And these are the results. These results are very close to the supervised learning. So even without labels, I can capture the apparent visual similarity pretty well. But what if I do have some labels? Because this woman image, I can label it as woman, I can also label it as dress. And it turns out for this query image, it takes the label of dress. So if I give you a label of dress, I'm providing my focus, my semantic focus. How can you incorporate such label information to the apparent visual similarity? With that, how can you come up with a metric that reflects both the apparent visual similarity and the semantic similarity? The fourth row is our results. Same idea. It's related to our unsupervised learning, but incorporating label information. By labeling this image as dress, this is on the test set, but there'll be other training images labeled as dress. After we learn with such supervision, it's really external. You can name an image in many different ways. But once that external guidance is given, the visual feature that's learned, pick out this puffy dress. It's not necessarily the same model in different poses. It's actually, all these so-called nearest neighbor search results share the commonality of puffy dress. Okay. And we show that you can, in the citations below, you can see that with the very coarse labels, our method can discover subclasses within each just based on visual similarity. Okay. The last thing I want to talk about is our goals in the SimCenter project. Earlier, I gave the schematic formulation going from building information model to structural model. The representation given to us is essentially a JSON file. You have these wall sections with all these fields and their values. And you have the SAM model, and the structural model is also is given to us as a JSON file. So remember the 6 steps. The first thing we do is to turn that JSON file and come up with a BIM feature representation. It's a numerical representation. Likewise, for the SAM JSON file, we extract certain features. We pass the file and come up with a numerical representation. Now, during training, I have these paired data from different structural engineers. I train a neural net to capture that. It's a supervised learning problem. Once I have that, at the test time, given a BIM JSON file, I extract the BIM feature, and that feature goes through the neural net. It will predict a SAM feature. And with that, I can recover the SAM file. I give the SAM file to OpenSea simulation software. And with that, I can simulate how the building would shake under certain conditions. And I can measure the simulated shake data against the ground truth field shake data and get a sense of how good the quality is. I can rate the quality of my SAM. Then with this information, I can learn a different neural net, because we can learn a model with this quality information in mind. Our final goal is give the BIM file, and I'll give a specific quality level. I can output the SAM that has the specific quality. I have high confidence in predicting that this SAM model will have certain, say, 80% proximity to the actual ground truth shake data. And another line of efforts is, because BIM file and paired BIM and SAM data are rare, takes time to collect. We have been wondering, how can we build up a large scale BIM model, a repertoire of BIM models? So another line of effort is to say, can I get this BIM model, these building properties automatically from a lot of data available? For example, Streetview photos, satellite views, maps. Can I use deep learning? I have camera pose, I have 3D models. Can I extract the number of stories in the building? Can I figure out the construction type? Can I figure out the height and other properties? There are public building data sets out there. For example, from San Francisco, there are building footprints. There are 100K buildings out there with height and GPS coordinates. With the GPS coordinates, we can fetch the street view or satellite views of that around that building, and that allows us to extract information. If we have public and available 3D models, we can get a detailed information on the 3D models. There are building permits with more than 1 million records. They have annotated the construction types, for example. This requires human expertise. And there's also land use records, and contains the year that the building is built, and the GPS locations. So if during training, we train on data of specific years, and we can cross-referencing the years built, the appearance the building takes, and come up with a plausible building model for a new unknown building just by the image itself. These are the potential applications and the potential utilities of deep learning in expanding the BIM data set for the SimCenter. And this is just an example of what this building construction type data set contains. They tell you which building is fire resistive, which is ordinary, which has wood frames. The numbers there indicate the number of stories. That's all. I'm happy to take any questions. And I understand there will be another webinar where you can post your questions in your domain, and we can discuss possible formulations and the solutions. Thank you.
Thank you, Professor Yu, for the presentation. And at this time, we'll have a question and answer session. Attendees, you're reminded to send your questions via the chat panel to the moderator to be relayed to Professor Yu. And so we have a few questions, if you don't mind. The first is, can you explain the supervised and unsupervised learning again?
Yes. Supervised learning is, remember, machine learning is about predicting Y from X. In supervised learning, during training, you know for a given X what Y should be. You have paired data X and Y. For example, for this image classification, during training, each image gets a label: cat, dog, tiger. Unsupervised learning, I don't have any labels. I just have images. So what you see in this example is this result. The second row of results is unsupervised learning. I don't have semantic annotation. I just have data, images. Yet through the unsupervised learning, I can learn a right feature representation. Based on that feature representation, I can pick out images most similar to the query. And that seemed to conform better to our judgment of visual similarity.
Okay. And the next question, the goal of machine learning, it seems, is to do something better than the current experts. Are you envisioning computers taking over the structural design of complex buildings, or maybe advising experts by learning from data sets that we're able to provide, such as the strength of materials?
So predicting the strength of materials. Right now in our BIM to SEM, we actually predicting what material property should we use. That can be done. If you have some annotated data during training, you have, given particular building, if you have material, it depends on what information you can extract at the input level and what you would like at output level. You can always try to regress X towards Y. The quality depends on whether X is indicative of Y. And I do think there's a lot can be done, can be achieved with deep learning. For example, we have a BIM SEM paired model. These SEM models are from a few structural engineers. It doesn't encompass a lot of varieties of structural engineers. But we are learning component models. What it means that, we are, instead of learning the full image, right? We are learning, say, the components like image patch model. Because of that, it allows us to apply this algorithm on some never seen image and understand it, interpret it. So the practical thing is I can have a mixed personality. It's a virtual identity out of the experts I'm learning from, right? Every expert has a certain way of doing this finite element model. Through deep learning, through the way you model, you can come up with a new structure engineers, right? So this is, I'm going beyond what's provided to me at the input level. I can limit my model to capture the paired training data. But through the choice of representation, through the choice of loss function, through the choice of tasks, when I formulate the problem, whether it's prediction problem, classification problem, segmentation problem, I can go beyond what's available in the training data.
Okay. Maybe to follow up on that is, when we have high dimensions for the output, how can we deal with it during the training? Is there a method in which we can reduce the output and do the training?
Yes. So, yeah. So you need to figure out whether the high dimension is intrinsic, right? People talk about you may represent in 1,000 dimensional space, but all the data points probably lie on just a sliver, right? It's just a so-called manifold, right? It's just some small space in that 1,000 dimensional ambient space. If that were the case, you can do a lot of transformation in representing the output. Let's say it's the simplest, say PCA, right? You can reduce the representation. You can find the subspace. And so instead of learning 1,000 dimensional output, you find the PCA, maybe everything can be represented by 10 PCA. So you just need 10 coefficients to represent each output. So instead of learning in 1,000 dimensional space, you can learn in the 10 dimensional space. And if the data supports that, you can certainly take advantage of that. And that usually, as you reduce the number of dimensions, you need less training data. You have much better prediction accuracies.
Okay. Maybe a more specific question to the BIM to SAM work you're doing. How do you define the loss functions for the BIM to SAM neural network? How do you score the generated SAM?
So I haven't got into the details of representation, but it's for BIM. You can think of the challenge there is, one building may have 10 floors, another may have 20. At the test time, maybe 15 floors, right? I've never seen a 15-floor one, but at the test time, I'm given a 15-floor. So I mentioned earlier about this component model. I'm looking at component, that's one. The other thing is about each, say the frame. We are decomposing the frame into these universal units, the cuboids. And then each structure can be represented by a collection of these primitives. And then we do some representation normalization. It becomes a fixed length vector. And a SAM feature, we do the same thing. We turn it into some feature vector representation. And going from BIM to SAM, we have a choice. We can go for just a regression. So now it's just one point in some dimensional space to another point in a second feature space. Or I can, if I know that these are, conjunctions, I can, just like the feature dimensionality reduction we just discussed, I turn the set of choices into few classes. I look at the bulk of the output data, I turn them into few classes, and then I can model it as a classification problem. So these are all the possibilities. In our work, we have used both. We use a regression formulation. We also use the classification formulation. And then at the test time, the image comes in, we turn it into a BIM feature, go through the neural net, come with a SAM feature. Once we have the SAM feature, we need to, do this translation into the proper JSON file. So you can think of it as encoding and decoding process, but we don't work with the raw text files.
Okay. How easy will it be to retrain the image to BIM neural net to learn new types of building images?
Yeah, so what we plan to do is we worked on two data sets. One is frame data set, the other is a wall data set. And we plan to put our code and with some readme.txt online to give you an example how we are doing this. Right at this moment, each translation process that's encoding, decoding requires some domain knowledge. A lot of text within this are useless, only some critical fields are relevant. So we do the extraction for this cuboid representation. It took us some time to figure out, that's a universal representation. As we see more and more different structural types, maybe the cuboid representation is insufficient. So we need to expand upon that representation as well. So this is open area. We are hoping that with more and more people joining in the modeling, when you see different choice of representation, maybe there's some universal representation emerge, some versatile representation that can be used for any type of structure elements. I think this requires exploration at both ends. That's why the AI team, we have people like us doing machine learning. They're like Frank Kincho, their structure have a lot of structure engineering expertise. We need this constant conversation to know what representation might be good, what is crucial, what may be relevant. So this is a really an application requires the close collaboration. And for this area, it's so new. I think we are still at an early stage to come up with a fixed representation. I would say that you might be able to just predict one JSON from another. That may require a lot of natural language processing expertise. Right now, I think what we are extracting, in a way, it's almost like a bare essential representation. The numerical representation we know that are relevant.
And Professor Yu, one last question. Are the AI algorithms available to the public? If so, can you give us some available groups that offer such algorithms?
The thing we are developing will be in the public domain. And for most, nowadays, for most computer vision papers, projects, it has been consensus in the community. People like to share their code. So if you find some techniques you like, for example, these two works we have, we share the code online. You can go to the GitHub repo and download our code and run on the features you extracted from your domain and run our code and get a sense of the how well it works for your problem. You don't, in a way, you don't have to write your code. You need to turn into the format the algorithm takes. I think maybe that's one reason that computer vision has made so much stride in the past few years with all these public benchmarks, for example, ImageNet, Dataset, and with this sharing of code, sharing of data, we have been able to make the most progress compared to other domains closely related, for example, medical imaging domain, where data tend to be proprietary and no one can reproduce someone's results. The data set is private. The algorithm, people don't usually put them online. Another domain is remote sensing. So for all these reasons, we have the culture of sharing code, sharing data, and sharing the project description online. And we intend to do the same for this project.
Okay. On behalf of the attendees, thank you, Professor Yu, for taking the time to share the background and examples that you've worked on in deep learning. To the attendees, thank you for your questions. And I want to encourage you to register for the follow-up webinar with Professor Yu on November 6th. Registration is available at the DesignSafe website. This webinar is going to focus on questions and answers for applying deep learning in your research. For example, if you have a data set and want to know what might be possible or what approach to take, Professor Yu is available to discuss some more specific applications. Please check the SimCenter's website at simcenter.designsafe-ci.org and check your inbox for emails from announce@DesignSafe-CI that will have registration links for additional upcoming SimCenter webinars. Thank you for your attending today. And again, Professor Yu, thank you very much.
Thank you for having me.